From a quiet plot of land to a fully living structure, every residential building begins as a question written in soil and is answered in concrete, steel, and precision. What you see as walls, rooms, and finishes is actually a hidden system of engineering decisions working in perfect coordination beneath the surface. Excavation opens the ground, foundations lock into the earth like anchored logic, and reinforced concrete rises layer by layer to carry invisible loads through carefully calculated paths. This is where civil engineering turns raw space into safe habitat. Watch the complete step-by-step journey of residential building construction, from site investigation and structural design logic to RCC frameworks, masonry systems, MEP integration, and final finishing, revealing how modern homes are engineered as resilient, load-bearing systems built for strength, safety, and time itself. Every successful building begins long before excavation starts. Site investigation is the first and most critical engineering activity in residential construction. The objective of site investigation is to understand subsurface conditions, including soil classification, bearing capacity, groundwater level, and potential geotechnical risks. These parameters directly govern foundation type, depth, and structural safety. Soil data obtained through boreholes, standard penetration tests, and laboratory analysis is converted into a soil report. This report is not a formality, it is a design document. Ignoring or misinterpreting soil data leads to differential settlement, cracks, and in severe cases, structural failure. Once soil suitability is confirmed, survey and setting out begin. Using total station or theodolite instruments, grid lines are transferred from drawings to the ground with millimeter level accuracy. Permanent benchmarks are established to control all vertical levels throughout the project lifecycle. Any small error in setting out propagates vertically and horizontally through the structure. Therefore, diagonal checks, access verification, and reference control points are mandatory engineering practices, not optional site activities. Excavation is not merely earth removal, it is a controlled engineering operation. The excavation depth and width are determined strictly by structural drawings and soil conditions. Different soil types demand different excavation strategies. Cohesive soils may stand vertically for short durations, while granular soils require sloped sides or shoring to prevent collapse. Safety of workers and stability of adjacent structures must be ensured at all times. Over-excavation is a common site mistake. It disturbs natural soil strata and reduces bearing capacity, forcing unnecessary remedial measures. Excavation bottoms must be level, firm, and free from loose or organic material before proceeding. In areas with groundwater presence, dewatering systems are implemented to maintain dry working conditions. No concrete work should be executed in waterlogged excavations, as it severely compromises concrete strength and durability. Excavation inspection is a mandatory hold point. Without approval of depth, level, and soil condition, the next stage must not begin. Plain cement concrete, commonly known as PCC, is laid as a blinding layer over prepared soil. Its purpose is not structural strength, but functional protection. PCC provides a clean, level, and non-reactive base for reinforcement placement. It prevents direct contact between soil and structural concrete, eliminating contamination and moisture absorption. Typically, PCC is placed in M7.5 or M10 grade with controlled thickness between 75 and 100 millimeters. Level accuracy at this stage directly affects reinforcement cover and footing behavior. PCC must be properly compacted and lightly finished, followed by curing. Poor PCC workmanship leads to uneven reinforcement placement, incorrect cover, and long-term durability issues. Though simple in appearance, PCC plays a silent but vital role in foundation performance. Reinforced cement concrete footings are the primary load transfer elements between the superstructure and soil. Their design and execution determine the building's long-term stability. Reinforcement placement must strictly follow structural drawings and bar bending schedules. Bar diameter, spacing, anchorage length, and cover blocks are non-negotiable engineering requirements. Adequate concrete cover protects steel from corrosion and ensures proper stress transfer. Cover deficiency is one of the most common causes of early structural deterioration. Concrete of specified grade is poured after slump testing confirms workability. Mechanical vibration is essential to remove entrapped air and achieve full compaction. Cube samples are taken to verify compressive strength at 7 and 28 days. Curing is continued to ensure hydration and strength gain. Most foundation failures are not due to design flaws, but due to poor execution, improper compaction, or ignored quality checks. The plinth beam acts as a structural tie between columns and helps distribute loads evenly at ground level. It also controls differential settlement between walls and columns. Prior to backfilling, anti-termite treatment is applied to protect the structure from biological damage. Backfilling material must be free from organic matter and placed in controlled layers. Each layer is compacted mechanically to achieve required density. Improper backfilling results in floor settlement and wall cracks after occupancy. A damp-proof course is provided above plinth level to prevent capillary rise of moisture. Moisture ingress at plinth level is a common cause of interior damage in residential buildings. Plinth level accuracy governs flooring levels and architectural alignment throughout the structure. The superstructure is the load-resisting skeleton of the building. Columns carry axial loads, beams transfer bending forces, and slabs distribute imposed loads. Column alignment and verticality are monitored continuously. Even minor deviations introduce eccentric loading, reducing structural capacity. Beam and slab shuttering must be designed to withstand fresh concrete pressure without deflection. Reinforcement continuity, lap lengths, and anchorage zones are critical to structural integrity. Concrete pouring should be continuous to avoid cold joints. Vibration and curing directly influence strength and durability. Deshuttering is performed only after achieving sufficient strength, as premature removal leads to excessive deflection and cracking. A reinforced concrete frame behaves as a unified system. Any compromise at one point affects the entire load path. Masonry in RCC buildings primarily functions as infill, but it contributes significantly to stiffness, thermal comfort, and acoustic performance. Bricks or blocks must be properly prepared, with bricks soaked to prevent water absorption from mortar. Mortar grade is selected based on strength compatibility, not convenience. Proper bonding ensures load distribution and crack control. Verticality and level are checked continuously to maintain alignment. Lintels, sill bands, and seismic bands are provided to manage stress concentrations around openings. Poor masonry workmanship often results in cracks, plaster failure, and water seepage, issues wrongly blamed on structural design. Mechanical, electrical, and plumbing services must be integrated with structural elements not imposed afterward. Concealed conduits and pipes are planned before concrete, and masonry works to avoid cutting structural members. Plumbing lines undergo pressure testing, while electrical systems are tested for insulation resistance and continuity. Uncoordinated MEP work weakens structural elements, increases maintenance costs, and compromises safety. Professional construction treats services as part of engineering design, not as afterthoughts. Plastering provides protection, aesthetics, and a controlled surface for finishes. It also acts as a barrier against moisture ingress. Surface preparation, proper bonding, and uniform thickness are essential for durability. Uneven plaster thickness leads to cracking and debonding. External plaster requires additional waterproofing measures and extended curing. Most finishing defects originate from rushed plastering and neglected curing practices. Flooring and painting represent the final engineering impression of the building. Flooring levels, slopes, and joint alignment must meet tolerance requirements. Painting systems follow a sequence of surface preparation, primer, and finish coats. Moisture content is checked before application to prevent peeling. Final inspections include leakage tests, functional checks, and snag list resolution. A professional handover includes documentation, drawings, and quality records, not just keys. A building is complete only when it is safe, durable, and ready for long-term service. Residential construction is an engineering process, not a trade activity. Quality is achieved through discipline, coordination, and respect for engineering principles. Smart construction is not about speed, it is about precision, responsibility, and durability.